Let's get started. So we're going to be doing exam 3 review today. This is primarily for Jesse's class, but it'll still apply if you're not in his. So if y'all could just scan the attendance and let me know when you're done, like a thumbs up or something. All right, let's move on. So we're going to start with substitution review, then we'll do some elimination review, then we'll do alcohols, some substitution elimination practice, alkynes, some alkyne practice, and then we'll do synthesis practice. So beginning with SN2 reactions, the most important things you need to know about this is that it's one step. And the most important thing is the strength of your nucleophile. So you need a strong nucleophile. And typically these type of reactions are done in polar aprotic. Can someone describe what a polar aprotic is? A polar aprotic solvent? Yeah. Yeah, no H bonding. So that's something like ketones or EMSO, common ones. And the reason we don't want that is because we need a strong nucleophile. So for example, we have Cn minus. If we had something that could do hydrogen bonds like this, it would actually weaken this nucleophile. So it would no longer be strong. So we do this in polar aprotic solvents. Additionally, it does inversion of stereochemistry. So say we have something like this. And we do an SN2 reaction with that, it'll form this opposite stereochemistry. Does that make sense? Okay. Moving on, this is the mechanism. Does a backside attack. We see that the CN attacks and it flips stereochemistry. Basically, what I just showed you. And again, it's done in acetone, something like that, which is polar aprotic because we do not want to weaken the nucleophile. And then this is the transition state. A way you can draw these is you draw the attacking molecule on the left and the one that was already there on the right. And then you draw dashed lines between those. And a way you can check to see if you drew it correctly is to check your stereochemistry. So in this example, it doesn't really matter, but say we had something like this. So what you would do is you'd label them 1, 2, 3. So that would be R. And then you draw it like something like that. And then you have Cn minus attacking, and your product would form this. And then in your product, you check your stereochemistry. So you have 1, 2, 3, be R, you flip it, it's S. So we go back to our transition state. If we count it, including the bromine and not the cyanide, we have 1, 2, 3. Then we have that, so that would be S. And then if we count it with the cyanide, we have 1, 2, 3, which would be R. So we know that that's incorrect. We need to flip some of these things around. And the easiest way you can do that is just flip these bottom two. So we put the hydrogen here, and we have our methyl there. So let's recheck it. So counting with the bromine, we have 1, 2, 3. That'd be S, but then you flip it, it becomes R. And then counting with the cyanide, you have 1, 2, 3, be R, then you flip it, S. So that's how you draw the transition state. Does that make sense? We understand that? Okay. So substrate effects for SN2, The faster reaction is typically the one that is less substituted because we're doing a backside attack. So when we're doing a backside attack, if it's less substituted, it can kind of get in there more easily. It's not really blocked off by stuff. Because if like we try to attack this one, it has a bunch of stuff in the way. It's like pushing it out. So it's no good. That also matters with beta carbon. See, if we try to do a backside attack, it's like, oh, there's stuff in the way. It's like, I don't like that. So it prefers this. How's my pacing? Y'all think I'm going too fast or good? We're good? Okay. So leaving group effects, you typically want a good leaving group. Good leaving groups are weak bases, electron acceptors like H2O, tosylates. These are a bunch of good examples. Typically, you'll see like halogen, like bromine or iodine, as well as something like OTS. Those are the most common ones you'll see. And then for bad leaving groups, most common one you'll see is an OH group or OR, basically just O with anything. Those are the most common bad leaving groups. And if you want those to be your leaving group, you need to do something to them because they're not going to leave on their own. So again, stronger nucleophiles lead to faster reactions. Strong nucleophiles are like this stuff. They're typically negative. Rate equals K times nucleophile times substrate. And the way I remember the rate is it's SN2. So it has two things in the rate equation. Solvent effects, this is something I covered earlier. So for polar aprotic, they can't do hydrogen bonding, so they're not going to stabilize charges. So these are good for SN2 reactions. Whereas things like this, polar protic, they can stabilize stuff. So if we were doing an SN2, which depends on the strength of the nucleophile, this would also stabilize the nucleophile, making it worse. So we don't use polar protic for SN2. All right, I'll have you do this practice. I'll give you all a few minutes for this. Thumbs up if you're ready to move on. All right, let's do it. So we look at SH. Typically the Na kind of just dips. So it's SH minus. If we use our table, we see that the substrate is secondary. There's two things attached to it. And SH minus does SN2 for a secondary substrate. So we know that this is SN2. And we can draw that. Would this flip the stereochemistry? Yes, it would. Yeah, SH. We understand that? Makes sense? Pretty simple, right? Yeah. It's the answer. Now for SM-run reactions, most important things to know about this is speed depends on the carbocation being formed. SM1 reactions are two steps. They involve the formation of a carbocation. So this typically involves a weak nucleophile and is often done in polar protic solvents. Remember, polar protic solvents, they stabilize charges. So this is dependent on how stable our carbocation is. So if we do it in a polar protic solvent, it's going to stabilize that carbocation and make it favor SM1. And this, it doesn't flip stereochemistry. I mean, it will, but it'll also form the other one. It forms what's called a 1-to-1 enantiomeric ratio. So it'll form something like this, as well as this. It forms both of them. And SM1 reaction, rate equals K times substrate. Remember, SM1, it has one thing in that reaction. Moving on, this is the mechanism. So first we start out with the group leaving. We need a good leaving group for this, and it forms this carbocation. Then we have a nucleophile that can attack the carbocation and form our product. Pretty simple, we got that, okay? And substrate effects. So this is opposite of SN2. Remember, for SN2, we wanted a less substituted leaving group. But for SN1, we want a more substituted leaving group. And that's because when we form the carbocation, it's more stable when it's more substituted. We see this is a secondary carbocation versus a primary. So this would be faster. Remember, tertiary is more stable than secondary, which is more stable than primary. This is like a key concept for SM1. Same thing for the beta carbon. And that's because when you form that cation, this could do like a, for example, methyl shift, which becomes a more stable carbocation. Leaving group effects, bad leaving groups, OH, again, same thing. Typically, OH will be our key bad leaving group. It's the thing you'll most often see. And good leaving groups are like halogens. You'll most commonly see Br, Cl, I, H2O is good, or ROH. And better leaving groups result in faster reactions because they'll form the carbocation faster. And this is also important because in the rate law, rate equals K times substrate. The substrate contains the leaving group. So a good leaving group will make it a better substrate and a faster rate. Pretty much what I just said. Nucleophile doesn't appear, doesn't really affect the reaction rate because as soon as the carbocation is formed, it's gonna go. It's trying to get there. So it doesn't really matter. It's gonna be really fast. The thing that's slow is the leaving group. And for these, we use polar protic solvents, as I've explained earlier. When you form that carbocation, these polar protic solvents can stabilize that carbocation. Remember, a more stable carbocation for SM1 will result in a faster reaction. Does that make sense? Okay. All right, here we have some practice. We ready to move on? All right, seems like most of y'all are ready. So for this first one, do we think it's SN1 or SN2? Yes, SN2. When you're doing these type of problems, it's very important to determine whether it's SN1 or SN2 first. So the first thing that could happen is we could just replace that leaving group. But another thing that could happen in this case, I don't know if y'all will have an example like this, but this is something that could possibly happen, is that the OH group would deprotonate that to form something like that. And then this could be used as a nucleophile as well to form this ring structure. Does that make sense? Do we understand that? Because OH is a good base, so it can deprotonate this OH. And then for the second one, this is SN1 or SN2? SN1, yes. So this involves the formation of the carbocation. And then the OH group will attack that, forming this. Do we have any questions on that? No questions? Okay. It's the key. For this one, when you form that carbocation, it is possible that resonance occurs. So you could get something like this also as an answer. Okay, now we're going to cover some elimination. So we're starting out with E2. E2 is one step. Remember, E2 is one step, E1 is two steps. I don't know why they named it like that. It doesn't make sense, but something you got to memorize. And remember E2, so there's two things in this reaction. It's based on the substrate and the base. And an important thing to remember is that the leaving group and the hydrogen need to be anti-paraplanar, meaning one needs to be on a dash and one needs to be on a wedge. So if we have something like can that do E2? You said no?
So let's substitute side. It's like a different base.
Okay, so yeah, anti-paraplanar, we see that the bromine and the hydrogen are on the same plane. They're both coming towards us. So we can't do E2 with that. A way you could do E2 with that is by rotating this single bond right here. So it'd give you something like kind of ugly, but that's what it would look like. It rotates it because these are on the same plane. They can't do E2. If we had something like can that do E2 as is? Yes, it can because they're opposite. So I've formed something like this. Does the anti-paraplanar make sense? They have to be opposite each other. And then reaction rates are faster with tertiary alkyl halides, which I drew right here, and they're slowest with primary alkyl halides, like that. And that's because the transition state is more stable with a tertiary. This is showing more of that anti-paraplanarity. I don't know if they're going to have you do it with a chair structure. They might. It's kind of evil, but if they do, you need the leaving group to be axial. So we see here this chlorine is axial. And the hydrogen also needs to be axial, but it needs to be opposite the chlorine in the sense that in this case, the chlorine is up, so the hydrogen needs to be down. So here, there, the hydrogen is down and axial. So you could use that one. There, you also have that. So it could go either way. But you can't use this one because that's equatorial. Does that make sense? Both need to be axial and one needs to be up, one down. All right, Zaitsev's rule basically states that the more substituted alkene is used when you have like a small base. So that's seen here. When you have something like OH, small base, it's going to form that more substituted alkene. Whereas if you have a big base like OT-butyl shown here, it forms the Hoffman. And that's kind of because it can't really get in there very well to get the hydrogen. It's too big. It's in the way of itself. And then for E1 reactions, there are two steps. So you have a carbocation, and this is dependent on only the substrate. E1, one thing in the reaction. And stability of the carbocation, very important. As always, as anytime you have a carbocation, it's always pretty important. So the way this works is the leaving group leaves. Then you have like a base that picks up the hydrogen and forms that alkene. That's shown right here. Again, reaction rate increases with the stability of the carbocation. Here's the table. I drew this out for you. Very good that y'all know this table. Pretty much have it memorized. It's very important. You'll use it a lot. It's not that hard to memorize it, to be honest. Like, I forgot it, and I've been drawing it every week, like one time for like 3 weeks, and I haven't memorized by now. Like today, I didn't need to look at my notes to draw that. So just draw it out a couple times, you'll memorize it eventually. All right, here we have some practice. Are ready to go over it? Yep. Okay, let's start. So OH, it's a small base, and we use the table. We see that it favors E2. So typically, when you have anything that's R O minus, it's always going to do E2 of some sort. But with primary and secondary, it could also do SN2. We see that there. With primary, it actually favors SN2, but it does a little E2. And with secondary, it favors E2 and does a little SN2. So anything with RO minus, it will always do some sort of E2. That will form this. Next, looking at KOT butyl, that's a reactant that you should know always does E2. There are a few that always do E2 and only E2, and that's DBU, DBN, and KOT butyl. And is KOT butyl big or small? Big, yes. So it's going to go on the less substituted side, forming this. And then I already said this, DBU is, and DBN, E2. So is DBU and DBN big or small? Yes, it's small. And that will form this. Does anyone know why it doesn't go there? Kinda. So here, this carbon has 4 bonds already, so there's no hydrogen. There's no beta hydrogen. It can't go over there. So it'll go like that. Any questions on this? Okay. It's the key. Here we have some more practice. I'll give you all like 2 minutes to do this. Are we ready to move on? All right, let's do it. So DBU, big or small base? Small base, yes. So DBU does an E2 reaction. Do we think it's going to go towards the left side or the right side? Left side. So you're saying this side? Why? Yes, that's right. This hydrogen is in the same plane as the bromine. They're not anti-paraplanar. And a way I said we could get around that earlier is by rotating the molecule. But with rings, you can't rotate them. They're pretty tense. So it'll form this. OH minus. Is this going to form on the green side or the red side? What do we think? Red side? Say green. Seems to be kind of split. All right. So a lot of you are probably saying red because the hydrogen is in the same plane, right? Remember, with single bonds, we can rotate them. So if we rotate this molecule, we can actually put it there like this, form something like that. It kind of rotates that single bond. It looks a little weird, but it rotates it. So instead of being like that, which is not the right answer, It'll rotate the molecule. Does that make sense? We understand that?
Yeah, so. Molecule, or do you just grab it?
Well, OH minus is a small base, so it's going to prefer to go on the more substituted side. So if we go towards that side, on the red side, it's only primary, whereas on the other side, it'd be secondary. Next one, KOT butyl, big or small base? Big base. So that will choose the more or less substituted side. Less, yes. And it can be like that. Is that what y'all got? Feel good about this? Any questions? No? All right, let's move on. It's key. Just went through that. So substitution versus elimination. Honestly, I feel like this is too much words. Just memorize the table. It's a lot simpler. You'll use it a lot. Carbocations formed with SN1 and E1. Remember, because they're two steps. No carbocation with SN2 and E2. E1 only occurs with tertiary carbons. Something that kind of stands out. And then SN1 uses polar protic because it stabilizes the carbocation, and SN2 uses polar aprotic because you don't want to stabilize the nucleophile for SN2. And then in SN2, you have the inversion of stereochemistry. And SN1, you have that mixture, 50-50 mixture. E1, no stereochemistry. And for E2, they need to be anti-periplanar. For E1, it doesn't matter if they're anti-periplanar. So say you have something like, and then you react it with H2O. You can still do E1 with this because it doesn't matter. You're going to form this carbocation right there, right? So for E1, it doesn't matter. But for E2, always make sure it's anti-periplanar. That's something we'll throw in there to trip you up. Here we have some more practice. For a tip for this, always determine whether it's a substitution or elimination reaction first. Are we ready to move on? Y'all feel good? All right. So for the first one, what type of reaction is it going to do? SN2, yes. So remember, with SN2, we have that inversion of stereochemistry, giving that as our product. What about for the second one? What type of reaction will that do? Yes, E2. Remember, O minus with R will always do some type of E2. And because we have that heat, we know it's definitely going to do E2. Will that double bond form on the green or the red side? Red side? Yes, because it needs to be anti-periplanar. This hydrogen is on the same side as the iodine, so we can't use that one. Gives us that as our product. Any questions on this?
Yeah, so heat overrides like the DMSO. Like DMSO would favor SN2, but like since there's heat, like the heat is greater than.
Well, I assume, so this already favors E2 a lot. So the DMSO and the heat probably almost cancel each other out, right? Does that make sense?
Probably around there.
Yeah, so it still favor E2 a lot more. Yeah. It's a key. Got some more practice for y'all. I'll give y'all a few minutes on this. Are y'all familiar with kinetic and thermal products? Y'all know what that is? So kinetic is the one that is faster, the faster product that is formed. And the thermal product is the one that's more stable. All right, y'all ready to move on? All right, let's do it. So T-butoxide, what type of reaction is that going to do? E2, yes. Is that big or small? Big, yes. I guess in this case, it doesn't really matter. It can really only go in one place. Something like that. What about for the next one? What type of reaction is that?
SN2.
It's a SN2? Why? I don't know. Yeah, just use the table for this. So it probably should be SN2, right? RSH.
I would say one, because you're a tertiary.
Tertiary, yeah. All right, so my fault. Tertiary, right? Tertiary substrate. Remember, I had y'all take a picture of this, so you probably have it on your phones. You don't gotta squint. But tertiary, and we have RSH. Usually when you see R on this table, it just means anything. So the R in this case is the methyl. So this is SM1, right? And kinetic, the one that's faster, is when you have this carbocation, it instantly gets filled by the nucleophile. That's our kinetic, right? See, makes sense, right? It's quick. It just instantly gets filled. And then for our thermodynamic, it's the one that's more stable. So with this tertiary carbocation, we can do resonance, pouring this. Right? And then we can have our nucleophile attack. Giving us that. Do you know why the secondary alkene is more stable than having a tertiary carbocation?
I would say for this one, it's like the alkene stability that's more important here because like the cation stability is what affects whether it's kinetic or not. So that's not what you look at there, but it's like how substituted your alkene is. Because here you have an alkene with three substituents, and here you just have one. Yeah, one there on that alkene. Does that make sense? So if you guys remember when we talked about like alkene stability, anytime you can get more substituents, it's a more stable alkene. And then whenever you can do on opposite sides for like E alkenes, that's also gonna be more stable than C. So that would be what determines your thermo product, if that makes sense.
Yes. What does it say is the group that's attached to that SHE?
That's gonna be, yeah, that's the methyl and then the sulfur group.
Any other questions? All right, let's move on. That's the answer key. And then now we're gonna do some alcohol review. I drew out all these reactions, the alcohol review reactions you need to know. They're all right here. I have them nicely organized for you. So when you study them, they're right here. There's not too many of them, and they're pretty simple. So first, remember, OH is the one that I really emphasized is a bad leaving group. It's the one you'll see most often used as a bad leaving group. So the first thing you can use is TSCl and pyridine, and that will make it OTS, which is a really good leaving group. So then we can do other reactions with it. Or you can use MSCl and pyridine, which will make OMS. I don't know how common MSCl is for you guys in your classes. I've never seen it before. So maybe you'll use it, but TSCl, super common. This is a mechanism. It's not really something you'll need to memorize. This is how you can do an elimination reaction with OH is by using a really strong acid like H2SO4 plus heat. And this typically will form it on the more substituted side. This is the mechanism for that. I think I remember drawing this mechanism once on a quiz, so this might be something you need to know. And the way it works, OH picks up that proton from the H2SO4, becomes water, which is a good leaving group. It leaves, and then that same water can be used as the base to pick up that hydrogen and form that double bond. Not too complicated, makes sense. And this is another alcohol reaction. You can use HBr. This is a pretty simple mechanism, is that picks up the H. Now will give us water, which is a really good leaving group. It leaves. Then the bromine can attack. Important thing to note is note the change in stereochemistry. Made a mistake here. It doesn't form the cation. It's a SN2 reaction. Like that. That's why there's the inversion of stereochemistry. This mechanism, just drew this out. Very simple one. You might need to draw this one out too on a quiz or exam, so it's a good one to know. All right, we have some practice. Remember, if you don't know what they do, I have all the reactions drawn out over here. We good to move on? Yeah, thumbs up to move on. Okay. All right, so going through this first one, after the first step, they'll turn it into an OTS. Which then becomes a good leaving group that we can use for a substitution reaction. It could also do an elimination reaction. It would actually favor an elimination reaction. But in this case, we're just asking for the substitution product. So the other product that could form would be that. And we get that inversion of stereochemistry because it's an SN2 or an E2. And then for the first one, we can kind of work backwards with this. We see that we have OET, which we know is probably doing a substitution reaction because we see it in the product. So we need it to be substituted with something. And we see that we have that tosyl chloride and pyridine, which all you guys know is it reacts with water. So we can just replace that with water, or not water, OH. Just like that. And we have that inversion of stereochemistry because remember, OET does an SN2 reaction. So it's going to flip the stereochemistry. Any questions on that? Okay. It's the key. We're going to do some more substitution elimination practice. So draw out the products and then determine if they are E1 or E2. Are we ready to move on? Thumbs up. Move on. All right, let's do it. So for the first one, is it E1 or E2? Yes, E2. And will it form the double bond on the green or the red side? Yes. And why is that? Yes, this hydrogen is in the same plane. What about the next one, E1 or E2? E1, yep. And then is it going on the green or the red side? Why did we say green? For E1 reactions, it doesn't matter. We don't care if it's anti-paraplanar. So it will actually form it on that red side. that. Yes. SM1? Yeah, it could be SM1, but in this question, we're just asking if it's E1 or E2. Yeah. Yes.
You draw the arrows.
Like the mechanism? Yep. So we start out with the leaving group, leaves. And that gives us this. And then we have a hydrogen here, which this will pick up and form that double bond. That makes sense? What about for the last one? E1 or E2? Yes, E2. Is that big or small? Yes. Get that as our product. Any questions on this? All right. So answers. This is wrong. It should be that. All right, here we have some more practice problems. Give you a few minutes for this. All right, let's go through this. So for the first one, SN1 or SN2?
SM1.
There are some twos and some ones. SN1 or SN2? SN1. Yep. And we see ROH, anything with that OH, and then R group is SN1. So we see that that will form a carbocation intermediate. And that carbocation intermediate will rearrange to form this intermediate, right? And then the OH will attack that, forming this. And then it will deprotonate it and it will form that as our final product. And remember, it also has the enantiomer. It forms a 50-50 mixture. Does that make sense? We understand that one? All right, moving on. Cn minus, or SN1 or SN2? Yes. Very strong nucleophile. So that will form this as our product. That one make sense? Okay. And the last one, SN1 or SN2? Yes, SN2. Because it's the same thing as O minus R, right? Whenever you see that O minus, we know that it always does E2 and it'll do SN2 when it's primary or secondary. And this is primary. So it actually favors the SN2. And that is one step. It will form this. Any questions? No questions? Okay. So answers. Here we have some practice. So for this one, you're going to circle the one that will make the faster reaction. And for SN2, what makes a reaction faster? What are some things that can make it faster? Less substituted, that's one of them, yes. So more stable carbocation, that's actually for SN1. What did you say? Yeah, stronger nucleophile. And there's one more. Yes. Good job, y'all. All right, try these ones. All right. Wait, what are you trying to explain to them? Maybe I can explain better.
For part three, the acetone's better than water, just because it's anaerobic, and I just don't know why, I just don't know it is.
Yeah, so water has these OH groups, which will stabilize this charge, making it a worse nucleophile. Remember, a better nucleophile makes the reaction faster. That make sense? All right, let's go through these. So for one, which one is better, the top one or the bottom one? Top one? Why do you say that? Yeah, better nucleophile. For two, which one? Top one or the bottom one? Bottom one? Why? Yup. What about for three? Top one or the bottom one? That is the bottom one. That's because the polar aprotic solvent, it's not going to stabilize that charge on the nucleophile. And we want a strong nucleophile. What about for four? Top one or bottom one? Top one. It is the bottom one.
How come it's the,
You know why that's the bottom one?
Yeah, so on the top one, if you were to. What were we doing for ethic or S1? So S2 specifically?
Well, yeah, would do.
This, well, okay, you can't do substitution on this because it's not. It's trigonal planar, so you can't like orient the molecules right to actually like kick it out of place, if that makes sense. Like, you know, you have to do a backsided attack to do the inversion of stereochemistry. Here you don't have stereochemistry except on your alkyne, so you can't like attack from the opposite side to kick it off because there's not an opposite side, if that makes sense.
I don't know if I've ever seen substitution on an alkyne as well.
So don't do that.
It's pretty weird.
Yeah.
What about for five? Top one or bottom one? Top one. Why did we say the top one? A nucleophile. That is one of the reasons. Is there another reason? Yeah, it's a better leaving group. Do we know why it's a better leaving group?
Higher,
Yeah, so it's like bigger, it has more electron orbitals, which can stabilize that charge better. Good job, y'all. Next one. I'm gonna go over alkynes. These are pretty similar to alkenes. It's just another bond. So we're gonna start out with nomenclature. It's been a while since we've done nomenclature. So for alkynes, it's pretty much the same as alkenes. You just add YNE on the end. So like here we have heptane. We're gonna make that heptyne. And then right before that is where you put the locant of the alkyne. And you just put the first number. So it'd be 1 heptyne. And then after that, you just add the substituents, same as we've always done. So we have a 4-ethyl and a 3-propyl and a 5-methyl. Remember, you put those in alphabetical order. So you have 4-ethyl, 5-methyl, 3-propyl, 1-heptyne. An important thing to note is that if you have a double bond present in the molecule with a triple bond, you're going to start your numbering at the double bond. The double bond is more important than triple bond. But if it's not there, you start it at the triple bond. And you want the triple bond to have the lowest possible numbering. So let's do some numbering and naming. So I'm going to do the second one with you guys because it's a little tricky. So first thing you do is you number the molecule. And we see that we have a double bond and a triple bond. So we're going to number it, making the double bond have the lowest possible numbers. So I labeled it like this with 1, 2, 3, 4, 5, 6, 7, 8. And then the way you would name that parent chain is it's 8. So it's octane, right? Then you put the alkene first, you put it in the middle, octene. You put it first because the alkene has priority, and then you put the alkyne like that. So that's the name of the parent chain. It's kind of weird looking. Normally, like if this double bond wasn't here, you could just name it like 2-octyne or 2-ine, right? You could name it as either one of those. Yeah, you go the other way. But because we have that double bond, you need to name it like this. It's pretty weird. And then we just add the methyl groups, 5,5-dimethyl. And remember, for alkenes, you need to state whether they're E or Z. Is this a E or a Z alkene?
C.
Very confident. It's E. Remember, Z is same. They're on the same side. So like that would be Z, right? But these are on opposite sides. So it's E.
You said you have to do ears but it's
For alkenes, for double bonds. Yep. All right. Why don't y'all try the first one? It's a little easier. Are we ready to move on? Yep. All right. So first thing you do, start out by naming your parent chain. So I'm going to number it like this to give that alkyne the lowest possible number. So we have 3-octyne. And then we have a 7-chloro and a 2-methyl. Remember, we put the substituents in alphabetical order. So we have 7-chloro, 2-methyl, 3-octyne. Could also name it like 7-chloro, 2-methyl, oct, 3-ine. Both are fine for this one. All right. Any questions on this? Feel good about that? All right. This is how you can form alkynes. You can use a double elimination of a dihalide, which was seen in this mechanism here. And it's usually done with excess sodium amide, which is a very strong base, very, very strong base. And then use water as your second step. And water is just used to pronate that alkyne at the end. This is hydrohalogenation and halogenation of alkynes. So basically, if you have an alkyne and you use bromine, Br2, excess, you'll get 4 bromines. Like that. Right? But if you use just one, one EQ is for one equivalent. You get something like that. Make sense? And then the same thing happens with HBr. You can also do this with HBr peroxides. So like we see here with HBr, it puts it on the more substituted side. If we use peroxides, it put it on the less substituted side. So for something like this. That's with one equivalent. If you did it again, it would end up with 2 bromines on the end. Like that. That makes sense? All right, moving on. Oh, have a good day. So we're going to look at hydration. Have y'all covered this in class? Yes. Do y'all use 9-BBN or do you use BH3? Use BH3? Yeah, that's what I thought. I've never seen 9BBN. Who uses that?
I think Albaniac might, I'm not sure.
Interesting. That's something to confirm with your professor. Most use BH3, I feel like. So what this does is it forms this enolate. Is that enolate?
Yes.
It forms the enolate, but you can't stop there. It will never stop there. So it keeps going and forms that, the aldehyde in this case. Does that make sense? Basically what it does is you have the triple bond, you react it with this stuff, and it turns it into a double bond with an OH group on the less substituted side. No, that's wrong. I drew it wrong. I said it right. OH group on the 1, 2, 3, 1, 2, 3. OH group on the less substituted side, right? And then that's not going to stay. It's going to form that. Right? Makes sense. Right? We get that? And instead of 9BBN, you can use BH3. A way you can put it on the more substituted side is it on this one? H2SO. This will put it on the more substituted side. So basically, instead of doing that, it does it like this. We use these reactants and we get this, which this can't stay. This is not allowed. It'll become this. And that's called tautomerization, is when it goes from this to this. We understand that? This is a tautomerization mechanism. You might be asked to draw this on a quiz or exam. So basically what it does is the double bond will pick up a hydrogen from an acid. And what that does is it forms this cation right here. That cation can do resonance with the oxygen, forming this double bond. And then this, which got its hydrogen robbed from it earlier, it's back to get its hydrogen. It gets its hydrogen back and you have the ketone. Make sense? And then here is how, what is this? That's basically the same thing. This is a very important reaction. This is like the only reaction you'll ever know, or not ever know, but the reaction that you'll learn in Orgo that can add carbons. Before, we've never added carbons. Most of those reactions, you're just adding different groups, different functional groups, OHs, bromines, halogens. This is adding carbons. And the first thing you use is NaNH2. And what that does is it deprotonates the end of that alkyne. So this has a hydrogen here. It takes that hydrogen. NH2 is a very strong base. It's right here. R2 N minus. Very strong base. Very strong. So it's going to take that hydrogen away. And this thing, think of it like a sticky end. It's just going to pick stuff up. It's a very good nucleophile. So if you have like this bromine, right? Bromine's a good leaving group. It's going to kick out that leaving group and act as a nucleophile, forming this. So when you're doing like synthesis reactions, if you need to form in like more carbons, you use this reaction. It's a very important reaction. That makes sense? We understand this? We've got a little time to copy this down. The NH3 is a solvent. It's not very required. Professor might ask for it, maybe not. Ready to move on? We got this. Acidity of alkynes. Terminal alkynes need a very strong base. That's what we're using our H2N as, very strong. And there's not a lot of bases you can use for this. You'll pretty much only see H2N. Here's reductions. So if you use H2 and palladium or a different catalyst, usually you use palladium, you should use that one. It's just gonna fully turn it into this, fully reduce it, right? If you use a poison catalyst, which is what Lindlar's is, you get the Z alkene. And if you use NaNH3, you get the E alkene. These two will be very important for synthesis later. These are ones you should know like the back of your hand. Don't confuse NaNH3 with NH2 that we saw here. They're pretty similar, but they do completely different things. That makes sense? We understand this? Again, I have all these reactions written down right there.
For these ones also, for this one at the bottom, sometimes you see the sodium metal with like a little like dot next to it. That just indicates that it's metal, not to be confused with like sodium when it's stabilizing something else. If that makes sense.
Yes, this is specifically sodium metal. All right, ozonolysis. So we've learned ozonolysis before. Before, what it did. Before, what it would do is it would split that double bond and just plug in oxygens there. It does something pretty similar with alkynes. So basically what it does is it splits it and it puts both an oxygen and an OH group on there. It forms what's called carboxylic acids. And then if it's a terminal carbon on the end, so that would look like something like that. Instead of being a carboxylic acid on the end, it forms this carbon dioxide. Those reactions are drawn there again. So let's do some alkyne practice. I know that some of y'all are not very familiar with these reactions, so please use the ones I draw. It'll help. You ready to go over this? Yeah. All right, let's do it. So an important tip when dealing with alkyne reactions, always count your carbons from your starting material to your product. It's very easy to get tripped up on your carbons. So with two bromines, we know that the first set is going to do this. 1, 2, 3, 4. 1, 2, 3, 4. So our first set is just going to add one set of bromines. And then the second set will add another set of bromines. Like this. And that is called bromination. Make sense? Moving on. This is missing a reactant. This should have HSO4. And what this does is, remember, it forms the more substituted enolate, and that tautomerizes into the ketone. And this is acid catalyzed hydrogenation. Does anyone want to try the last one? What do we think the reactant should be for that?
Let's do H2 like.
Yes, H2 palladium. Because that fully reduces, and that's called reduction. Any questions on these? These are kind of just reactions you have to memorize. Key. All right, so I'm gonna go through this mechanism with you guys because I don't think we really have before. So there's two equivalents of Cl2. We have two of those. So with the first one, this will attack the chlorine, but the chlorine will also attack it. It fights back. And what that forms is something like this, right? And then the chlorine from earlier, it attacks there. And this goes there. And that forms something like that. And then we know this reaction. We've done this before. It's just Cl2 across the alkene. So that attacks, and it also attacks back. And that forms something like this. And then we have another chlorine, which will attack here. Remember, it's attacking there because the chlorine is going to attack on the more substituted side. And that gives us our final product as this. The arrow there.
Arrows would be flipped. I think on that one, that should be right here. Top side.
Yeah. Yeah. These arrows should go like that. Is this something they'll be quizzed on?
I don't think so.
Yeah, I don't think y'all will be quizzed on the mechanism of this.
I was looking back through like notes for in class and it said that this isn't super well understood. So I don't think they need to
Okay.
know it.
Yeah. The professionals don't understand it. Y'all probably don't need to either. That's the mechanism. I think these arrows should go like this. Yeah. Here we have a little practice problem. Go ahead, give it a try. These are kind of like synthesis problems. You won't see too much of these on the exam, but there might be some. I want to go through this. All right, let's do it. So first thing we're going to do is count our carbons. So here we have 1, 2, 3, and here we have 1, 2, 3, 4, 5. So we only know one reaction that can add carbons. And that is first by deprotonating it with NaNH2. So that forms that. Remember, it's like that sticky end. And then we can add our carbons with this. So we have our 1, 2 carbons. Because here we have 3 carbons and we're adding those 2 carbons. So that's our second one. And that will form that. And then we just reduce it with H2 palladium. Any questions on that? All right, moving on. So we see that we have these two ketones, carbonyls, not necessarily ketones. These are kind of like aldehydes actually, but the reaction we know that does that is O3, and this is DMS, and that does that on an alkyne or alkene. So it would be something like, I'm gonna count carbons, 1, 2, 3, 4. So 1, 2, 3, 4. So that's what we have. And then something with H2 Lindlers will make this. So H2 Lindlers, it doesn't really change the amount of carbons. It just reduces the alkyne. So we can just draw the same amount of carbons, but with an alkyne. So we have 1, 2, 3, 4. Same amount of carbons. Does that make sense? For these type of problems, it's really important you like understand what each of the reactants do and like have a good grasp on them. Any questions? No? Okay. Moving on. So answer key. We're gonna draw the mechanism for this. I haven't went over this, so I'll go over this with you guys. So basically, it's just like a SN2 type reaction. This attacks that carbon and this leaves. It's pretty much all there is to it. Pretty simple. That's how the mechanism works. And that's how you add more carbons in the synthesis question. Answer key. All right, we're going to do some synthesis practice. This is like a roadmap. You'll definitely see one of these. If not on exam 3, you'll see it on the final. And there'll probably be like 1 or 2 of these. So just like, I'll zoom in a little bit. Try to fill in those boxes. If you don't know how to fill it all in entirely, just start out with stuff you know. For example, like this first step, HBr with an alkene. I'm sure most of you guys know that one. So just try starting out filling the ones you do know. Y'all want to go over it? Yes. All right, let's do it. So let's start out with stuff that we do know. So HBr, it will just form this on the more substitute side. Pretty simple. Do we know what reactant goes here? Yes, and then H2. And then this arrow just means that it's going to go there. And then this does like a nucleophilic attack, like a SN2 type reaction, forming this, right? And then NaH2, we already seen what that did here. So that's going to form this. And that bromine comes back here to form this. Makes sense. And then H2 Lindlers, is that going to form the E or the Z? Alkene. Z? Yes. So that will look something like, I'm going to draw it over here because it's not going to fit in the box, but something like that. It just reduces it one time. And do we know how to put 2 OH groups across a alkene? What reactants do that? OSO4? What else? You need some more stuff with that. That's close, yes. Keep going. You got it.
Water.
Yeah, so you can use OSO4, then NaHSO3, comma H2O, and that'll work. Or you can use MCPBA H3O plus. Yeah. So you're saying instead of this, we use Na and NH3? Yeah, you could do that. Yeah. Yeah. Because there's no stereochemistry here, we can use either one of these. But do we know the difference between MCPBA, H3O plus, and OSO4? Which one is syn? OSO4, yes. Which one's anti? Yeah, so that's the difference. And if there was specific stereochemistry, then it would matter whether you use NaNH3 or H2 Lindlers. It would give you different products. This is the key. Here we have another one. I'll give you a few seconds about this. Y'all think this would work? You say no? Why no? Yes. This is a very strong acid, HBr. So this is just gonna pick up that and form that. So they won't do the reaction. Make sense? It's a very good nucleophile. So it's really willing to pick stuff up, especially from a very acidic molecule. This explanation, kind of wordy. All right, here we have a synthesis practice problem. Are we ready to go over it? Yep. All right, let's do it. So let's work backwards on this. We see that there are two OTS groups that were not previously there. We know they probably did not go on there as OTS groups. So the first thing we can do is make them not OTS groups. Turn them back into OH groups. And then if we compare our starting material to that, we see that there is an OH group that pops up right there. We have a reaction that can put an OH group on the less substituted side of an alkene. And if we look over here, we see that an OH group goes right there. And we can put an alkene right there through KOT-butyl. That forms that. And now all we have to do is use that reaction that puts the OH group on the less substituted side of alkenes. So the reaction that does that is BH3, AHF, H2O2, and AOH. When y'all use this one, does he also require water as a reactant, or is it just H2O2, and NaOH? Okay, that's what I thought. But that's how the synthesis would look for that. Any questions? You ready to move on?
Is the OH, they attaching to the less substituted side?
Yes, of the alkenes. So like the less substituted side is there and there, right? And
How come they do the less substituted side?
because this like reactants, they put the OH on the less substituted side. BH3, THF, H2O2, and NaOH. It's a chapter 8 reaction. Any other questions? It's the key. All right, here we have another one. This one will also take 3 steps.
And then you microwave with no pen.
I love the honesty on that.
I thought it was gonna be like the other one, and I was like, never mind.
I'll give us a good old backwards arrow. Well, that's not even backwards, but you know the vibe. It's still forward, but I think we need to work back one step first. So if I work one step back from the final product, if we look here, we have 2 alcohols present. Do we notice anything about the alcohols? Yeah. So what does that mean? How do we make that? Oh, we're so poor. Newman. Just throwing out names. So yeah, we want OSO4 and then was NaHSO2, SO3, and H2
H2O. That's an ugly H, but you know. Alrighty.
Wait, why? Why are?
Because we have these two alcohols. What do you mean? Wait, what? I'm lost. Yep, they came from somewhere. And if we look right here, we got them in the last step, right? So probably in the step before that, we were making those two alcohols there.
Yeah.
So if we look, they're one bond apart. So that means that they're diols. If we think back on those, we don't know if they're syn-diols or anti-diols, so that doesn't matter. But we just need to know a way to put two alcohols across a bond from each other. So if we think back to chapter 8, we can do that with OSO4 and the NHSO3. But what else do we have to make that happen? Alkene. Exactly. So yeah, we need our alkene and our starting material there to then add those two groups across the alkene. So now we need to get from having our alkene over here in the starting material to over here in this intermediate.
So if you could walk into the, get into the.
Yes. You said it so confident and quick, and then I got scared. Yes, so yeah. Well, no, DBU is a small base.
Wait, is DB in different? I think all the D's are the same.
Yeah, DBN and DBU are both small. If you look at them, yes, torpedo is the big bulky one. That's like the only one that we know that's big and bulky. But yeah, we'll just use DBN, DB, whatever one you want. It don't matter. Yep. So then, okay, we add DBN, and that gives us an elimination, adding on our more substituted side. So where did we have to have a leaving group before that?
So BR was the
Where?
on the end of the net. No, actually, no, where the 5 on is.
Which side of the 5 on?
Well, wait. When you do it, you move it here. Yeah, I'm not. And no, actually, I guess the right. So
What are my rights and left? The left. Yeah, it's the left one. Good call. I don't know my rights and my lefts that well. Yes. Wait, what did you say? Yes. Yeah. Okay, so then how do we go from the alkene that we have to adding this bromine? Yeah. Yep, we need HBr, which is gonna form a little cation, and then she's gonna get all stabilized in our tertiary position, and then we're gonna have the Br attack there. Does that make sense? Any questions on this one? Okay, we got there. So that's what counts. Alrighty, guys, there's our answer key. It's like the same thing. Okay, here's the last one. Play. So yeah, there's just 2 of you guys, so we can just like work through this together. Bingo, ozenolysis. Yep. So yeah, if we have 2 ketones that are present, that's pretty suspect that we're probably doing ozenolysis. Or 2 carbonyls. So yeah, here we have a ketone and aldehyde. Or you know, if you just have 2 carbonyl groups present, you probably did ozenolysis. I'm gonna say probably because like maybe you didn't, I don't know, but most likely. And then what do we add? Water. So if we do oxidative cleavage that cleaves what?
Well, it's given obviously.
So you're, you wanna start where? You kind of could, honestly.
I knew the opposite, you know, opposites, so.
Wait, what'd you say? So we already have CL, so
Well, you don't add that unless you.
yeah. If we had like an alkene and we were trying to form a like chlorine on there, then we could add HCl. Yeah, but here we want to do like the opposite of that. So instead we're kicking off the chlorine. So how do we do that?
I know you use like the T, MCl when you have OH, it's a good leaving group, but then also a good leaving group, but I don't know what you use.
So so it's already a good leaving group. We don't need to make it a good leaving group. What do we add to get rid of it? What's another word for getting rid of the leaving group? Not quite. That'd be like a proton. We're kicking it off. It's getting starts with eliminated. Yeah, so this one's an elimination. Yes. Yepperoo. Yeah, we're gonna add DBU, DBN, whatever. That is not even kind of the right shape. Okay, hold on. Okay, and then where does that add our ketes? What? Our alkene? In yes. Right there. And then to double check that we did that right, we can go and count our carbons and then count them on the product and see if that looks right. So if I start over here and I count 1, 2, 3, 4, 5, 6. We still have 1, 2, 3, 4, 5, 6 over here. But look, we've got 1, our little methyl sticking out, 2, 3, 4, 5, 6. We have the same number of them. And then here, if we look on 2 and 3, we're cutting open that right there. Well, okay, I switched my numbers around, but you get the vibe.